Hello. Yes, hi. Welcome to the latest in our series of talks on advanced topics in programming languages. Today we're very lucky to have Thomas Wouters, who's here to talk to us about features that are currently available in Python, but are advanced features. Last week we were very lucky to have Guido van Rossum talk about upcoming features. Today we'll be talking about existing features, right? Yes? I wanted to, as always, this is the latest in our series of talks, I always want to make a pitch so that people will actually give talks of their own. It's a really useful thing to do if you have specialized knowledge or if you have interesting knowledge, to share that knowledge with as many Googlers as possible and potentially even the rest of the world. So please come and see me and we can set up a talk and you can give yet another in our series of talks here. And with that, I will turn it over to Thomas, who shall give a very interesting talk. Thank you.
Is this on? Right. Although there's an echo, but. So I'm going to give a talk about advanced Python, which is not an easy subject in that there's a lot of Python that can be considered advanced. I'm not sure what your level of advancement is, so I'm going to cover basically everything from the start until the end, and we'll see how far we'll come. These are the subjects I'll be covering. I'll certainly be explaining about the Python design, objects, iterators and generators, and hopefully decorators. Everything after that is a bonus. I'm going to keep the pace pretty high, so if there's any questions, just wave your arms and I'll stop and explain. But if everyone can keep up, then we can probably cover the more interesting topics at the end as well. And if there's specific interest in any of the topics, especially, for instance, Unicode, I can skip over the advanced stuff and jump right to Unicode. So first about Python. Python was developed by Guido as a middle system language between shell scripting and system programming. So it was intended to be easy to use by normal programmers, but still allow more complex structures than a shell scripting language. It turns out that it's also convenient for library programmers, people doing the actual programming for end users, because you can hide a lot of smarts inside of objects or modules and just expose a very simple API to end users. This has gotten progressively better with later releases of Python. There are multiple implementations of Python. CPython is the one everyone uses except for those that are developing the others. Jython has been around for quite a while, is actually in use by a lot of people, but not as much as CPython. IronPython and PyPy are still actively being developed, although IronPython is apparently very usable. It is designed by implementation in that if you don't come up with an implementation of a feature that you want implemented, it's not going to happen. But it's not a slave to the implementation, and it doesn't mean that if you implement an idea, it'll get in. It's still a very designed language. We have feature releases every 1 to 2 years. It used to be every year or so. Now the last one was in the works for 2 years. And there's a lot of bug fix releases as well. Important note about the feature releases, if you do not get any warnings in using a particular minor release, upgrading to a newer minor release, the one following that minor release will almost certainly work. Anything that changes semantics or possibly breaks code will be warning for at least one release. And bug fix releases have a similar requirement that you can always upgrade to a newer bug fix release of the same minor version, and nothing will break that wasn't already broken. Important in realizing how Python works is that everything is runtime. Even compile time is actually runtime. As you may know, there are cached files, PYC files, that are cached bytecode. That's basically borrowed runtime, someone else's runtime that you can skip. Also important is that all execution happens in a namespace, and that namespace is actually a dict. It's a dictionary object with keys and values. Modules, functions, and classes all have their own little namespace, and they don't affect other namespaces unless they explicitly do so. And modules are executed top to bottom. Scripts start running at line 1, and they run all the way down to the end or until loops or whatever make them wait. So in that regard, it's very much like a script. When you import a module, it does the same thing. It just starts executing line 1 and runs on down until at the end, and then the import is done. And another important aspect is that the def and class statements don't define a function at compilation time. It's a runtime thing. It actually happens when that statement is reached. So some more about functions and classes as well, because they're important features. At compile time, which is runtime, the code for the function will be compiled into a code object. It's a separate object from whatever the rest of the code is compiled into. And then at def time, when the def statement is executed, the code object will be wrapped into a function object along with whatever arguments it takes, any defaults to those arguments. And essentially, def is an assignment operation. If you look at the bytecode, you'll see that it just uses the same bytecodes as normal assignment operations. So here's an example of a function. The red part is the actual def statement that gets evaluated when it's reached, including the part in blue, which is an argument default. That part gets evaluated at the moment of def. So the foo object is constructed, or the foo function is called if it's a function, at the moment that def is being executed. And the green part has been compiled at that time, because compile time has been in the past. But it's not being executed until later, which is when you call the function. So this is when you call the function. There's an inner function in there. So what happens is that the green lines you see here, they've been compiled into their own code object. And when you call func, the inner func gets created at that time. And again, the default argument, or the defaults for the arg3 argument is evaluated at the moment you call def. If you look after the definition of inner func, you'll see that arg1 and arg2 are reassigned. That means that whatever arg2 was will be assigned to inner func's arg3, and not whatever it is at the moment you call inner func. However, inside inner func, we also use arg1, which is using nested scopes, which I'll be mentioning later as well, which means that it'll be using the outer function's arg1, and that will be whatever arg1 is at the moment you call inner func. So there's a very big difference between those two uses.
Question?
Yeah.
That very final line, was that evaluating inner func, or was
No.
you pointed to the function?
It's just returning the function object.
Okay, thanks.
So it's not calling anything. Only the parentheses do actual calling. Yeah.
In future, could you repeat the question?
Sorry, yeah.
What video conference that is?
The question was, is the last line actually evaluating inner func? It is not. It's just returning the function object that is inner func. So class statements are very similar, but also very different. A class statement is followed by a block of code, a suite, that's executed when the class statement is reached right away. It is, however, executed in a separate namespace, a dict again. And then after that code block has been executed, the namespace is passed to or is used to create the actual class object. Any functions that you define inside the code block then get turned into methods by magic, basically. And well, as people who've already programmed in Python will know, the self argument, the this for Python, is passed implicitly when you call a method, but your methods still have to receive it explicitly as the first argument. And an important thing to realize is that the code block in a class is actually a normal code block. You can do whatever you want in here. For instance, at the top, I create a class attribute, which is just something stored in the class, the result of calling func. I define a method, which is just a normal function, but it takes self as first argument, and it assigns to an attribute of self when it is called. I also define a helper function, which just does some silly arithmetic, and call that helper function inside the class block itself to calculate or recalculate the class header. And at the end, I delete helper because otherwise it would end up in the class. And since it doesn't have self as first argument, it wouldn't do very helpful things. Other important parts about Python, variables aren't containers like in other languages. They're not allocated memory that you can use to store data. People often say about Python that everything is an object, and they also sometimes say everything is a reference. That's both true, but both are not true when you apply them to variables, because variables are not objects and variables are not references. Variables are only labels. Everything concrete, everything that allocates memory, everything you can toss around is an object. And whenever you hold an object, whenever you store it anywhere, you're actually storing a reference. You don't actually own an object, you only own references to an object. Variables don't have type information. They don't have information on the scope of a variable or how many objects live around or when they were created. The only thing they do is refer to an object, and that's it. If you want to look at it from an implementation standpoint, it's a dict. It's a dictionary mapping names to objects. That's it. So scopes, also related to namespaces. Python has a very simple two-scope rule, which is actually 3 scopes. Names are either local or they are global or built-in. Local means it exists in the current function or class or module, but it doesn't exist outside. Global means it exists in the current module. It doesn't mean it exists everywhere, just in the current module. And built-in is a special namespace that is used by built-in functions that you can actually modify. It's just a special module that you can modify yourself if you want to. When the Python compiler examines a function and compiles a function, it keeps track of whatever names you assign to and assumes correctly, because by definition, those names you assign to are local. You can change this by using the global declaration, which is the only actual declaration Python has. But don't do it too often. It's usually a sign that your code is incorrect. All other names that the compiler finds are either global or built-in. And the lookup is it looks in global, and then it looks in built-in. So if you have a global of the same name as a built-in, all the code in the module will find the global of that name instead of the built-in. You can actually use this on other modules as well. If you import a module and then assign to an attribute of the module, you'll be assigning to a global name in that module. And you can mask whatever it thinks is a built-in name by assigning to that attribute. There's also a trick with nested scopes, which were added later in Python, I think in Python 2.1. Where you can, as I pointed out before, you can refer in an inner function to a variable in an outer function. But that is only read-only. You cannot assign to a name in an outer function. This isn't really a mechanical problem in Python. It would be possible to assign if we added it, but there's no syntax to say, I want to assign to an outer scope variable. Global only assigns to the global name and not to outer scopes. Apparently, Py3K might be getting, Python 3.0 might be getting syntax for this. So I mentioned modules. Modules are there to organize code. They're very convenient because they have their own namespace with global names. They also keep the rest of the modules tidy. They're always executed on first import and then cached in sys.modules. This cache is just about everything that you import in your program. And it's also the only thing that keeps track of what you have imported. So if you toss something out of sys.modules and import it again, it'll get executed again. Import is just syntactic sugar, just like basically everything in Python is syntactic sugar. It calls the under import under built-in function. If you want to do an import of a module whose name you have in a string object, you use under import. If you want to replace under import, you can just write your own function and replace the one in the built-in namespace. Another trick is that sys.modules does not have to contain modules. It's a mapping of name to whatever object you want import to return. So you can toss in any old object in there, and then importing that name will return your object. Storing none in sys.modules just means this module couldn't be found. So if you want to prevent a module from being imported, you can insert in sys.modules none under that name, and it'll raise import error whenever you try to import it. Python objects in general are described in various terms. Mutability is a common one. That means the object is changeable. Lists, for instance, are mutable. Tuples are not. Mutability is very important in Python because everything is a reference. If you have a mutable object and you end up changing it by accident and changing it for everyone, that's rather inconvenient. So you have to keep in mind whether objects are mutable or not. Fortunately, this mostly happens by accident correctly anyway. A related concept is hashability, whether you can take the hash of an object. In normal operation, mutable objects are not hashable, and most immutable objects are hashable. For instance, tuples are hashable, but they're only hashable if all their values are also hashable. Hashes are being used just for dicts and sets right now, so any dict key has to be hashable, and any set item, anything you want to store in a set, has to be hashable as well. But it's not inconceivable that more stuff uses hashes. And then there's the imaginary abstract base classes that are often referred, saying that an object is phi-like, or it's a sequence, or it's a mapping. Those are abstract concepts that are somewhat like protocols or interfaces or whatever you want in another language, but they're just informal. They're just saying whenever an object is sequence, it has the sequence operations implemented. You can look in it, you can iterate over it, et cetera, et cetera. Some of them are overlapping. For instance, sequences, mappings, and files are all iterable, so the iterable interface applies to all of them. And actually, all of the objects you define, all that you're defining is implementation of syntax. Python defines syntax, and you can plug in whatever implementation you want in that syntax. And you don't do it by, in other languages, you say you implement the less than operator. In Python, you say you implement the less than operation, so that it can be used even when you're not actually using the less than operator. Here's a short list of hooks that Python supports. I'm not going to go over all of them. Most should be common enough. And the one thing that's worth mentioning is conversions. You can define a few hooks that define how your object gets converted to other types. That just works for built-in types, of course, because the hooks don't exist for arbitrary types. But most arbitrary types that want to do something like this can just say, if you have an under foo method, I'll call it to turn you into a foo object if I want to. But it's not very common. These things are not Python hooks. These things you cannot configure on your object. Assignment. Assignment is an operation that changes the namespace and not the object. Since an object is just a reference to an object, you have no control over where your references are going. Another thing you cannot control are type checks. You cannot control when people are comparing your type or doing is instance checks, you cannot control what they get as a result. Related identity comparison, the is operator, it checks whether two references are pointing to or referring to the same object. You have no control over that. And or, and not are Boolean operations, and they just call the one truth value test that your object can implement, and you have no control over what they actually return. As some may know, and or in Python return one of the two values, whereas not returns always a Boolean. And method calls. You cannot define in a single operation whatever will happen when someone calls a method on you, because methods are getting an attribute followed by calling that object. They're two separate steps. So in order to implement method calls on your object, you would have to implement getAttr to return some go-between object, and then have that go-between object do something when it's called. Sorry. So on to some implementation details in C. This is just applies to C Python, of course. Python objects are implemented in a struct that holds various bookkeeping information like ref counts, the actual type that an object is, as well as arbitrary C data. It can be pointers, it can be ints, it can be an array, whatever you want. Types are what describes what an object is and how it behaves. They're a separate struct, which is also a PyObject struct. The arbitrary data in a PyType struct is the function pointers and various other things that describe the type. The PyObject structs are not relocatable. You cannot move them around once you've given them out to anyone else. It's a block of memory that's allocated, and that's it. If you want to move it around, you have to destroy the object, which means you have to get rid of all the references to it. This also means that variable-sized objects like lists that have a portion that needs to be reallocated and might move around are just use an extra layer of indirection. It's just a pointer stored somewhere in. And of course, because it's C, it doesn't have ref counting by nature, so ref counting is done manually. Whenever you receive a reference, you incref, and whenever you toss one out, you decref. It sounds simple. It can get quite complicated, but the Python C API is mostly clear enough that it's not too hard once you get used to it. Another feature that is done reasonably manually is weak references. Weak references are references that get informed when their object goes away so that they can do some cleanup and not crash. The weak references are just callbacks, basically, in the PyObject struct arbitrary data. One of the major problems with ref counting is reference cycles. That is, two objects that refer to each other, causing them both never to be cleaned up. Two objects referring to each other is, of course, the simple problem. The complex problem is a huge loop of objects referring to objects and everything. Python has a cyclic garbage collector which keeps track of objects that might participate in cycles, for instance, lists and dicts, and walks them every now and then to find object groups that are not reachable through anything but themselves. And then it cleans up the entire cycle. This is all done in C. If you write a C extension or a C type, you don't usually have to bother with it too much. There are some methods you have to implement if you want to participate in cyclic GC when you think you might be participating in cycles. So in Python, when you have an object, what do you have? Well, you have an object that has two special attributes. The under-dict attribute, which is a dictionary holding per object data, and you have the under-class attribute, which refers to the class. And like in C, the class defines behavior. And in newer Pythons, the class is actually a PyType object, and it all matches. The way to define the behavior is not through function pointers, because Python doesn't have function pointers. It's with specially named methods, methods that start and end with under. Those are special to Python. They're not special because they get allocated differently. They're just special because some of them get called by Python automatically in some situations. You can define your own under methods and use them whenever you want. There's nothing special in that regard. It's just some of them signal to Python, this needs to be called whenever that happens. In general, you should not be calling another object's under methods yourself, not directly. You should always use them through whatever mechanism wraps them. So for instance, if you want to have the string representation of an object, you shouldn't be calling object.under_str under. You should just be calling str object. Another feature of Python is that class attributes, that is attributes of the class object, are also reachable through the instance. If you do instance.adder and it's not defined in the under-dict, it'll be fetched from the class. And the class might have parent classes, so those get searched as well. And of course, in Python, the whole point of Python is that you don't have to do stuff that Python can do for you. So ref counting, weak references, and cyclic GC are all done automatically. You never have to worry about them. Typical Python code does not use type checks, because partly because it was never possible until a couple of years ago to subclass built-in types. So pretending to be a built-in type meant that other people would not have to use must not use type checks, or you could never pretend to be a built-in type. It's also very convenient. It just means you can pretend to be whatever type you want, implement the right methods, and it'll just work. The C layer sometimes needs specific types. If you want to multiply a string by an integer, it needs to actually have a string and an integer, or there won't be any multiplication in C. So the C layer has conversions. When it wants an integer, there are special methods that say, I need an integer at this argument. It'll convert whatever gets passed in, and it'll convert whatever gets passed in to an integer or a string and do the multiplication that way. If you really must use type checks, for instance, because you're faking C code or you're wrapping C code or whatever, use isInstance instead of type. Checking type for a specific value means you only accept objects of that type, whereas isInstance does proper instance checks so that someone who does subclass, whatever type you expect, works the right way. Functions become methods by magic in Python. It happens when you get an attribute of an object, or rather, when you get an attribute of a class through an object. Whenever you get an attribute of a class that is a function, it gets turned into an unbound method, which is a method that knows it's a method, and it knows which class it belongs to, but it doesn't know which instance. So when you call that method, it knows that the first argument you pass must be an instance of that class, and it'll complain if it's not an instance of the right type. Of course, that type check uses isInstance. So when you have a method's unbound, or you have an unbound method, you can pass a subclass of whatever class it expects, and it works. Bound methods, on the other hand, are methods that know their instance, and they will be passing that argument automatically, so you call them without the first argument. You start at the second argument, and it all looks normal. So any questions so far? No? All right, on to iterators then. So iterators in Python are really simple. They're helper objects for iteration. They encapsulate, if you will, the iteration state, and they're created and used automatically. If you don't want to bother with them, you don't have to, and it all just happens by magic. If you do want to bother with them, you can do a lot of fun stuff with them. Even more so if you combine them with generators, which I'll be talking about next. Iterators are two methods, under iter and next. Notice that there's no under around next, because next is actually intended to be called directly sometimes. So there's no under around it, or people would think that they shouldn't be calling it. Because they're simple, iterators in Python are not rebindable, they're not reversible, they're not copyable, none of that. They're the lowest common denominator in iterators. There are, however, ways to write reversible iterators if you want. You can just write your own iterator class and add methods to rewind or reverse or whatever. You can also just nest iterators. And iterators themselves are iterable. They're just, actually, an iterator is required in its own under iter method to return self, or it wouldn't be an actual iterator. So in the example I have here, I explicitly create an iterator over a range, which is a list of numbers from 0 to 10, not including 10. And then I call zip on it, which takes a number of iterables and takes one element of each iterable and wraps it in a tuple and stores that in a list, which it returns. So I create a single iterator, pass the same iterator to zip twice, and as you can see, zip takes one element of each iterator, consuming the iterator as it goes, and ends up with having two elements at a time, basically, from the original list of 0 through 9. So generators are a convenient way to write iterators. They're lazy functions that get executed as you iterate over the result, basically. Generators use the yield keyword instead of return. It works very much the same way, except after a yield statement, execution continues there the next time you call it or the next time you iterate. The function with yield in it will return a generator. It will return an iterator that you can loop over. And this is terribly convenient for under iter methods, because you can just write what you would expect and it'll just work. In Python 2.5, generators were complexified, and they can now also receive data, and you can use them to build coroutines very easily. Nothing you cannot also do with 2.4 and earlier iterators, just more conveniently and with extra magic. There's a lot of generator-like iterators in the itertools module, which is, I think, new in Python 2.2 or 2.3. There's a whole bunch of stuff in there that you can use to chain and filter and whatever with iterators that is really convenient for chaining various combinations. So here's a generator example. The bottom function is map as, you may know it, except it only takes one iterable. the built-in map function. It creates a list of results from applying the function to every item in the iterable. In the bottom, there's a 2-line function that is the generator version, and then there's a 1-line function that is the original map implemented in terms of the generator. As you can see, you just basically lose half the function if you use a generator, because you generate items, each item on the fly, and you return a generator instead of an actual list. Any questions?
Would you define what a coroutine is and how you would do it in Python?
Can I define what a coroutine is and how I would do it in Python? A coroutine is a routine that is basically like a generator. It stops execution, passing data to someone else. But where a generator returns results to its caller, a coroutine returns results to someone else, another function. So you can have two routines where they both consume the output of the other, and then the end result is handled data. How you would do them in Python? Well, as I said, you can do them in Python 2.5 with new sending data to a generator thing. Before 2.5, you would write a class that was itself an iterator and just write it in bits and pieces. And it wouldn't be as convenient as coroutines in actual languages that have coroutines, because you don't have a single block of code. You have a whole bunch of separate pieces of code that get called at the right time. I wouldn't bother implementing them in Python right now. Maybe with 2.5 out or 2.5.1 out and people getting used to the new stuff you can do with generators, we'll get actual coroutines in Python. Yeah.
That was like if generators are lazy, I you can spin, define a generator over something that's infinite and only yield a finite number.
The question was, if generators are lazy, can you write a generator that loops infinitely and just keeps on yielding results as long as you ask for it? Yes. Yes, there.
Then you just ask for a finite number.
Well, do you ask for a finite number? You can. If you use the itertools module, you can slice iterators. You can say up to so many items in this iterator. And it'll return an iterator that starts consuming the original iterator until the slice ends. But you don't have to do that. The iterator is something you loop over. So if you have a loop that loops over two things at once and it stops whenever a condition is met, if you don't, you can just loop over an infinite object and rely on the fact that your loop will end itself for other reasons than that the iterator stops. There's actually a number of infinite iterators in the itertools modules, like itertools.count, which starts counting at 0 and just keeps on counting forever and ever, unless you stop for some reason. So on to decorators. Decorators are syntax in Python 2.4 for a feature that's been around forever, which is function wrapping. Decorators are just functions, or callables rather, that take a function as argument and return a replacement callable, or they can return the original function if they want. However, the syntax means that it can get confusing if you have a decorator that also has to accept its own arguments, because then you have a function that should return a callable that should accept a callable and then return the original callable. So we'll see some examples of that. Another problem is that because functions are special when they're attributes of a class, they become methods. When you have a decorator that returns something that's not an actual Python function, but something that acts like a Python function in most regards, it won't get turned into method unless you implement the same magic that methods or that functions have that turn them into methods, which is unrun or get, which I'll maybe explain later. So if you write decorators, make sure they're methods, or make sure they're functions, or they won't get turned into methods. And well, as I said, simple concept, but the devil is in details, and we'll see about that. Here's a simple decorator. It's a spam decorator that says whenever the function that you decorate, the sing function at the bottom, is called, it actually calls the wrapper function at the top, which loops for 10 times calling the original function. So in this piece of code, the original function gets called 10 times, and there's no return value of the actual function call, which there isn't in the original either. Here's an example of a decorator with an argument. The decorator is spam10, which is spam is no longer the decorator, it's rather the decorator generator that takes a number, which is the number of times to repeat. And then in spam, we define the decorator function, which accepts the function as an argument, and then has a wrapper function which calls the original function, and then return wrapper, and then of course we return the decorator from the decorator generator. So that all looks okay. I mean, it takes some getting used to, the nesting and everything, but there's another problem. What about introspection? Maybe Python users don't care about the name of their function, but some tools do, like PyDoc, for instance, which is the Python documentation tool. It actually looks at function objects and looks at their name and their signature and their doc string and whatever. And because we replace the original function, when you ask for the documentation of sing, it'll actually say it's called the function wrapper. And it has a signature of star args and star keyword args, and it has no doc string. That's probably not what you want. Another thing is that if you have another decorator in there, you can chain decorators that changes attributes of the function. Those changes will go away because you're not doing anything with the attributes of the function. So some people write code like this, which is the original spam with a repeats argument with the decorator function in there, with a wrapper function in there. And then after defining wrapper, we assign the name, the doc string, the module, and the dict of the original function back to wrapper, so that all those things will actually be the same for the new function and the old one. And assigning dict like that actually works. You can copy, it's not a copy, it's a reference assignment. The original function, all the original function's dicts or attributes will be accessible in the wrapper function. And when you assign to either one of them, it'll appear in the other one as well. They just share their attribute space. Now, this is not the easiest way to write a decorator. So in Python 2.5, in the functools module, there is a decorator for decorators that does this for you. So you have a decorator that you apply to decorator or to decorator generators, and then that decorator-generated decorator gets applied to whatever function you have. So as you can see, the devil is in the details. They can get confusing somewhat quickly. Any questions? All right. How are we for time? We got it. All right. New style classes. When I say new style classes, when anyone says new style classes, they actually mean old new style classes, because they were added in Python 2.2, which was released, I think, 6 or 7 years ago, something like that. They're old. And it's a unification of the C types that I explained and the Python classes, because before, or actually still, in classic classes, instances and classes are distinct C types. There's a C type called class object or class obj that implements all the magic that I talked about turning methods into, or turning functions into methods. And there's the C-type instance, which makes sure that instances work as expected with the under dict and everything. So they're separate types. And if you ask for the type of an int, it'll say it's an int. But if you ask about the type of any class that tries to be an int, it'll say it's an instance. So you have no way of checking all that. And another problem with the original approach was that you cannot subclass built-in types. So Guido worked in Python 2.2 on unifying C types and Python classes, and the end result is pretty good. You can mix them and match them and everything. It worked good. But it only works because a lot of new general mechanisms were added. They were all necessary to bridge the divide between C objects and Python types, and things that you assign from Python have to be inserted in as a C data type in a C struct rather than as a Python object pointer. Classic classes are still the default. So if you write a new class and you don't specifically make it a new style class, it'll still be a classic class. And that was for compatibility reasons, because there's a lot of stuff that's slightly different between well, a lot of stuff. There's a couple of things that are slightly different between classic classes and new style classes, mostly with multiple inheritance. And you can check if any class, or actually any instance of a class, is an instance of a new style class because it inherits from object instead of nothing. So you can actually do is instance my thing object, and you'll know that it's an instance of a new style class. The first of the mechanisms that I'm going to explain is descriptors. Descriptors are a generalization of the magic that happened with functions to turn them into methods. A descriptor is any object that lives in the class namespace, the class attribute space. So it's an attribute of the class, and that has under get, under set, under delete methods. It doesn't have to have all of them, I think. You can just do with under get or under set or under delete for specific operations. Whenever an attribute is attempted to be retrieved from an object whose class has an attribute with a descriptor in it, those methods on the descriptor will be called, and the result of those calls will be passed back to the object. Same for setting, it'll call the set method, no result of course, and deleting, it called the delete method. The delete method is not called under del under because that was already taken for some other hook apparently. It's now the method behind, the mechanism behind methods. So if you want to have a function-like object that behaves the same way as functions do becoming a method, you can do that by defining under get, under. And it's also the mechanism behind property, which is a trick of hiding accessors behind normal attribute access. So here's an example of properties. I'm not going to give an example of actual descriptors because it's too boring and you won't be using it anyway. But here's a property. We have a class, we define a function, getProp. It takes a self argument, even though it's not going to be a method. It takes a self argument. It does some stuff there to return whatever the value is of the actual property. And then we wrap it in property and store it in a local, in a name that'll eventually be a class attribute. Oh, I see I have an error right there. So we instantiate the class. I should have had foo instead of x there. And then we do foo.prop. Foo.prop calls the getProp. And because it's a property, even though it's not a method because it's just a function inside the class block, the property type knows that it needs to pass the instance, for convenience, the instance that it actually is called onto the function that wraps it. If you look at this, you can say, oh, this can be a decorator too. And it's true. You can just say @property at the top of def getProp, except that property takes multiple arguments. You can also pass a setProp and a delProp if you want to. I didn't do it in this example for brevity. But if you just have a getter, you can just say at the top @property instead of prop is property getProp at the bottom. Any questions about this? All right. So the other general mechanisms, kind of related, they're also descriptors, class methods and static methods. Before Python 2.2, Python only had instance methods, that is normal methods, methods that take self as the first argument, they got called in an instance, and if you try to call them on a class without having an instance, you get an error. So in Python 2.2, we got class methods and static methods. Class methods take class as the actual class object as the first argument, and that's terribly useful. I'll show why in a moment. Static methods take no magic argument, and they're not very useful. Even though Java and C++ programmers coming to Python often say, oh, I need a static method for this, generally not. They're only useful for one particular thing, and I'll show that in a minute. So here's a class method. Again, if you're using Python 2.4, you can use class method, @class method at the top for the decorator syntax. If not, you'll have to use it at the bottom. So say we have a fancy dict that's a subclass of dict, and we define a method to create a dict from a set of keys with a single value. So we don't have to generate this list of key value pairs. We can just say, generate it from keys. So what I have here is we create a list of that key value pairs and pass that to the class. And because it's a class method and gets the actual class passed, we can call it on any subclass of FancyDict without anything in particular happening in the subclasses, and it'll create a subclass of FancyDict instead of a FancyDict itself. So whenever you think, oh, I should have a static method and I'll do something with my own class, you should actually use a class method and do something with the first argument. Now, this is a rather silly example because Dict already has this exact thing implemented. There's already a fromKeys method that is a class method in the Dict type, and it's very useful whenever you subclass Dict, which is not too often. Anyway, at the bottom, it's shown what happens when you use it. So static methods, they're not very useful. The main use is protecting dependencies from becoming methods. When you use dependency injection, as I do here in the example, you don't know what you are actually injecting into your class. If it happens to be a method, or if it happens to be a function or something that does something magical when used as an attribute of a class, this won't do what you want it to do. It won't do the same thing as calling sendMail.sendMail, where I'm now calling self.sendMail. So you can wrap it in a static method to prevent it from becoming an actual method. That's the only thing I've ever seen that made sense for using static method. Although, as we'll see later, Python actually has a static method itself, which is a good example of something that should have been a class method. Another new feature, under slots, which is for omitting the under-dict attribute for arbitrary attributes. It basically prevents you from assigning arbitrary attributes to another object. It reduces memory use because the dict isn't allocated, and it's a more compact form to store the same number of attributes as a dict, but it's not going to be much faster than a dict, even for a few attributes. The main reason to have it is when you want to emulate or actually implement immutable Python classes, like we have immutable types, where you don't want attributes assigned to them arbitrarily. And here, well, there's a tiny class for showing slots right there. If you actually try to assign to something other than self.value, either in init or anywhere else, it'll actually throw an exception, except for stuff that's already in the class. But I mean, under init, the def statement won't be throwing an exception, of course, because Python knows that it's already there. Another new thing in Python 2.2 is the actual constructor. Before Python 2.2, there was just under init, which is an initializer and not a constructor. It gets called after the object has been created, and it's your job to initialize it and set the right attributes and whatever, but the data is already there. The object's already there. So under new is called to actually construct an object, allocate memory for it, make sure it's all right. In Python, it's used actually just for implementing immutable types, because if you have an under init to set attributes, it's too late because the type's already been created, so it can't be immutable if you can assign to it an under init. So you need to do it in under new. And this is the example of a static method that shouldn't actually be a static method. It cannot be an instance method because its job is to create the instance, so there's no instance to be a method of yet. So Guido made it a static method before he added class methods in the development cycle of Python 2.2, I think. It could have been a class method, but, well, it's too late now. It's a static method that takes the actual class as first argument, and you need to pass it around explicitly whenever you call the super classes new. When you want to actually implement under new, you generally always call object under new or your superclass under new to do the actual allocation, because there's no other way to allocate memory in Python. However, your under new method or static method can also return existing types, existing objects. You can just return any object you want from under new. Whereas under init either has to return self or return none, because there is nothing else. You can't actually change whatever it returns. Under new, you can return whatever you want, and that's the result of instantiating your class. There's one caveat there. When you return an instance of your own class, whether it's an actual instance of your class or a subclass of your class, the under init is still called, even if it's an already created object. That's because Python can't know that your under new is returning an old object or a new object. So it always calls under init. Of course, if you return something that's not your type, that's not a subclass of your type, it knows that it's already been initialized, so it doesn't call under init. So here's an example of an under new wrapping an int, which is an immutable type in Python. We set slots to the empty list so it doesn't get arbitrary attributes. And then in under new, we take the value, which is whatever our constructor was called with. We modulo it so it doesn't go past 255 or 256 or whatever. And then we actually create self by calling the parent class method. As you can see here, it's a static method because even though we're calling it on a class, we're passing the class we were passed as well explicitly. Any questions so far? Yeah.
How do you make an object immutable? I mean, how do you define a class and make sure it was immutable?
How do you create a class and make sure it's immutable? By not providing any of the things that that mutate the object. So, for instance, this is an easy example because int is its own value. So you're not storing anything in the value. We don't accept arbitrary attributes, and we let our parent create the object, and it's done. If you want to not subclass a built-in immutable type, you have to do a lot more work because you need somewhere to store the data and then provide properties to read the data but not write the data. That's basically how you create. So you do the same thing as here, and you have some magic in here that sets a hidden variable, basically, that then properties can get out, but nobody else can get write access to. It's not easy, and it's usually not worth it. Mostly Python classes are just implemented in terms of existing types. And if you want an immutable type, you either want something that is int-like, string-like, or tuple-like, and you can just subclass int, string, or tuple and be done with it. Any other questions? All right. Is there any interest in metaclasses? Shall I mention them? All right. So metaclasses are this theoretically satisfying and mind-boggling concept where you can draw all these graphs between what a class is and its metaclass and what the class of the metaclass is and then what objects it's an instance of. The general idea is that the metaclass is the class of a class. It's the type that a class is. It's whatever implements a class. And of course, the metaclass is an instance of something, so the metaclass has a metaclass. And they're all, in Python, the base metaclass is called type. And type's type is type. And type is actually an object. The parent of type, parent class of type is object. And all objects have a base class that's object, so you can see how it gets confusing. Of course, the type of object is type, so you can draw very funny graphs that way, but it's all, it doesn't matter, because in Python everything is simple, and you can just say the metaclass is the class that creates the class. So, of course, it doesn't apply to type or object because they're created secretly in Python by magic. But every other class you define, its metaclass is that whose job it is to create the class from that namespace that is the code block of the class. So if we go, if we go back to all the way up to the class here, this is all done before the metaclass is even looked at. And then when this piece of code, the blue parts and the green parts are all compiled and nicely wrapped up in a namespace, executed, nicely wrapped up in a namespace, then that dict is passed to the metaclass along with the name and the parents, whatever you want to subclass, and it says, create me a class and return it. And then the result of that instantiation is your new class. So it's practically simple. And whatever you want to use it for in Python, you can use it for. The stuff that you normally define in a class to define how an instance of the class behaves, you can do the very same thing with the meta class, and it'll define how the class behaves. So the magic that creates, for instance, functions, which is hidden in the class, the stuff that calls descriptors, which is hidden in the class, is actually called by getAttr or getAttribute, which is, probably should have mentioned. Under new and under init are called to construct the class and to initialize the class. That all happens the same way you would expect. So you can override them and you can do as many things as you want. The thing they're most useful for is post-processing a class, just doing some wonderful renaming or mangling or other stuff with a class after it's been defined, before it's visible to any other Python code, without requiring an explicit post-processing step. As I said, you can do evil stuff in getAttr or getAttribute if you want. It's probably not worth it. It'll just make your code much more complex. So here's a Metaclass example in Python. We subclass type because it's convenient, and I think it's necessary as well. You define an under new, which is the static method as usual. I forgot to mention, you don't actually have to explicitly make new a static method, but you can if you want to. The Metaclasses under new gets past the class that is actually ourselves, because it's a static method of ourselves, or a class method of ourselves. The name of the class that needs to be created, the bases, which is a tuple of the bases that are named in the class statement, and the dict, that is the namespace of the code object. It's just a dict with attributes. So what we do here is we go over all the attributes. We skip any that start with under because we don't want to, by accident, do the wrong thing with the magic methods. And then we name mangle whatever attributes are left over by appending or prepending foo under to them to make them look funny. We delete the original attribute, and then at the end, we call the base class new with the same arguments, but with the modified attributes. And then to use the meta class, you have to explicitly tell Python to use a different meta class than whatever's the default, which is type. You do under meta class, under is mangle type in the class dict, or if you want, at the top of the module. Now meta classes get inherited, so if you subclass mangled class, you automatically get the mangled type as meta class. If you want a subclass and have a different type, or a different meta class, your meta class has to be a subclass of your superclass's meta class. So if I wanted to have a more mangled class with a more mangled meta class, I have to subclass mangling type to get a more mangling type and have that as my meta class. So any questions there? Yeah, sorry, that's a typo. It should say mangling type at the bottom and not mangle type. Yeah.
I seem to remember that Django uses metaclasses somehow to provide a nice API. Is that true?
Yes.
But you know what they do?
Yes. I don't have an example right now. I have some Django code, and it's very interesting how it works in Django. Sorry, the question was, Django uses metaclasses, and how is that done? Django has an API where you define a class with various attributes to describe your data model. And then you can have some extra classes inside the class to describe admin options and display options and whatever. What it does is it actually, just like this, it goes over all the attributes that were the result of executing the code inside the class statement and examines them. And the order doesn't matter to Django for the most part, but where it does order, it abuses the fact that when compiling a class or executing a class, it executes top to bottom. So it calls a field, let me see, you do, a field is a particular type, and the type is an instantiation of a class. So you say field is in field. and field 2 is char field. And it keeps track of in what order those types were created by keeping a global counter, for instance, so it knows which order the fields are in the class statement. That's about the only magic thing that the Django thing does. And then for the rest, it's just examining whatever's in the adders dict that gets passed to the metaclass to write down the SQL that's whatever the database backend needs to store and whatever options there are, et cetera. Does that answer your question?
Yeah.
All right. Any other questions? All right. So I'm going to cover multiple inheritance unless everyone here goes, no, don't ever use multiple inheritance. All right? So multiple inheritance in Python and in other languages is something that's frequently argued, whether it's good or not, or sane or insane. Well, it's generally not a good idea, but occasionally, especially in Python, it can make stuff a lot easier. New style objects have a different way of doing multiple inheritance in that they use the C3 method resolution order, which is an algorithm described, I think, in a Dylan paper describing how to do, when you have multiple inheritance, in particular involving diamonds, where multiple superclasses inherit from the same superclass, how to handle that correctly. And the algorithm is pretty simple. It just goes a depth first, left to right search through all the classes, but then it removes all duplicates except the last one. So if a class appears 2 times, it'll be visited not the first time it appears, but the last time it appears. And in Python, we also have a conveniency object called super, which can help you continue method resolution. All your parent classes are visited after you are visited, and all your subclasses are therefore visited before you're visited. But they might not be the next base class. If your superclass might not be the next superclass to be visited, and your subclasses might not have been visited right before you. That's rather important to realize. So calling your base class method directly, saying my parent.foo, whatever, is never right, because there's always going to be some situation where that'll do the wrong thing and skip classes when visiting methods. So the way to do it in Python is you have a single base class with a full interface of whatever your tree is going to implement, so that any object can always call whatever method it wants to call within that tree on any other class within that tree. But in usual cases, those functions will probably be do-nothing functions. They shouldn't raise errors, because then you can't safely call them all the time. But they should, if anything, they should do nothing. The signature of those methods should never change, because you cannot know which order classes will be called in. If you have to change the signature of a method in a particular part of the multiple inheritance tree, you should have a second master, basically, in the multiple inheritance tree and make sure that it's a separate section of the multiple inheritance tree. And then you should use super everywhere you want to have anything from a base class, anywhere. And that can be annoying, because all of your code has to follow it in all of the classes, and you're usually not the only one developing all those classes. So you have to convince everyone to use super everywhere. And as I can show here, using super is not actually convenient right now. You call super passing this class, the current class, the class you're coding in, and the instance or class, if you have class methods, that you were passed, you were called on. That returns a proxy object, and then you can use that as if it was self to call the original method. It's not too convenient, and I hope we'll have syntax for doing super calls in Python 3.0, maybe sooner, but I'm not holding my breath. Any questions about this? All right, I'm going to cover Unicode then, if we have time. This is my last time. So Unicode, it's a somewhat longer topic, though. No, just twice as long as the previous topic or whatever. So Unicode is a standard for describing characters. The way byte strings describe bytes, you say A is represented by 65. In Unicode, you say A is code point 65. And there's no relation between Unicode as such and bytes on a disk. In Python, that means the old str type, the string, holds bytes. It's a byte string. We call it a byte string nowadays. And Unicode objects or Unicode strings, they hold characters, which is for ASCII is actually the same thing. But for non-ASCII, it's entirely different. Unicode has no on-disk representation as such. So if you want to store Unicode in disk or even in memory, you need to use an encoding. Python internally uses either UTF-16 or UCS4 encodings, or UCS2 and UCF4, depending on how you exactly define what Python does. But it uses either 2 or 4 bytes to represent each character. Whereas byte strings, they always use 1 byte for every character, or byte. When you have a byte string and you want to have a Unicode string, a Unicode object, you have to decode the byte string into Unicode. And if you have a Unicode string and you want to store it somewhere, or you want to pass it over to the network, or you want to write it to disk, you have to encode the Unicode into bytes. A convenient encoding is UTF-8, and some people confuse UTF-8 with Unicode. For instance, Postgres, the database, has an encoding called Unicode, which is actually UTF-8 and not Unicode. It's one of those mistakes many people make, but UTF-8 is not Unicode. UTF-8 is a Unicode encoding, and it's a Unicode encoding that looks like ASCII to all Americans or people who don't care about accents or funny characters, but it can actually encode all of Unicode. And it does so by basically screwing Chinese and Japanese people by having all of their characters be like 7 or 8 different bytes. So in Python, Unicode is pretty convenient, except where it mixes with strings. You can have Unicode literals, which look just like string literals, except you have a couple of more escapes. Besides the normal \x escapes and \o, and \0, I mean. You can have \u, which is a short Unicode escape, and a \U, which is a long Unicode escape. The short U has, as you can see, 2 bytes, and then the long U has 4 bytes. And the long U isn't really necessary until you start working with the higher code planes that were added last to Unicode and everything. Also, instead of CHR, the char, to create a single character, you have unichar, which creates from a number any character, any Unicode character. And we support in the compiler, at compile time, Unicode names. You can use \n and then in the curly braces, the name for any Unicode code point. Unicode defines all these names. We have them all in the interpreter at compile time. That actually results in a single character Unicode string with a euro sign in there. It's a single character in Unicode, but when you encode it in an encoding that supports the euro sign, it'll look actually an entirely different character or multiple bytes or whatever. If you want to do these name lookups in reverse, if you have a character and you want to look up the Unicode name, the Unicode data module does that for you. If you have the name and you want the actual character, Unicode data does that too. So Unicode objects, they behave exactly like strings. It's very convenient. You can slice them, and you're actually slicing characters instead of encoded data. The length is right. You can iterate over characters. Everything's great, except when they mix with non-ASCII byte strings. When they mix with ASCII byte strings, Python will automatically upgrade the byte string into a Unicode object, which is with the ASCII encoding. So that works for ASCII byte strings. But if there's a funny character in the byte string that's not ASCII, it'll blow up because it tries to interpret it as ASCII and it sees that it's actually not ASCII and it doesn't know what you want to do with it. So don't do that. Another problem with the Python approach is that the decode and encode methods of strings and Unicode objects are generalized. They don't just do encoding to byte string or decoding into Unicode object. You can actually convert strings into strings and byte strings into byte strings and integers into whatever you want, or 2 integers. It's inconvenient. And I'm not entirely sure if that should be fixed or not, but it's inconvenient when you only care about Unicode. On the other hand, they do have convenient features. So using Unicode in Python is very simple. Never mix Unicode objects and byte strings. It's a very simple rule. If you do that, everything will be great. Except, of course, it's not always easy not to mix byte strings in Unicode. If you write libraries, you might get past a string when you don't expect it, or you might get past a Unicode object when you don't expect it. If you write your application, you have to make sure that anywhere you get a string, you get it as a Unicode object, or you get it as a byte string and you translate it yourself. So decode, the best way to do it is decode byte strings into Unicode when you get them, and encode Unicode into whatever output you have when you're outputting. And of course, you have to remember to use the right encoding. So you have to remember what the encoding would be like when you get input or send output. And there's no way to detect an encoding, because it's just bytes, and there's no marker in there that says this is UTF-8 or this is Latin 1 or whatever, or UTF-16 for that matter. And it all looks vaguely familiar when you're actually looking at the bytes, but that might not mean that it's the correct thing to decode with that encoding. Fortunately, if you can figure out which encoding to use, Python does have some conveniency functions and modules. The codex module in particular, codex module has an open function that behaves like the built-in open function, except it takes an encoding and it'll automatically decode data as you read from it. So when you read from codex with open objects, you're actually reading Unicode, and you write Unicode to it, it'll automatically encode it into whatever encoding you passed in. If you want to wrap existing streams like sockets or files you partially read, you can use codex.getReader or getWriter to transform on the fly transform the stream from byte strings to Unicode or the other way around. And lastly, when you do write stuff like that and you're debugging your code and there's some problem with mixing Unicode and byte strings, pay attention to the exceptions, because there's two exceptions you could get. There's Unicode decode error, which you get when decoding a byte string into Unicode goes wrong, and there's Unicode encode error, which is the other way around. And if you use str.encode, so you're trying to encode a byte string into a Unicode encoding, what it'll actually do is silently try to decode the string first into Unicode and then encode it with the encoding you gave it. So that actually tries to apply the default encoding, which is ASCII, to a str. And even though you call str.encode, you will be getting a decode error if it ends up that str is not an ASCII string. So that was it. That was all my topics. I'm glad we went over all of them. Here's some more information if you want. Descriptors, metaclasses, and super are all described in Guido's original Desker intro tutorial for Python 2.2, which is still very relevant. Iterators and generators are well described in Andrew Kukling's tutorial on functional programming. You don't have to follow the whole thing if you don't like functional programming, but the parts about iterators and generators are very good. And if you want to learn about writing C types, the standard documentation is a great source, as well as the Python source. The actual Python modules are all in the same API, and they're a very readable source, even if I do say so myself, and it's highly recommended. And always, the Python standard library and the Python C code are all great sources. That was it. Any more questions? I can put them up somewhere.
How about the previous presentation about the upcoming? I didn't see that one.
Sorry?
The previous presentation, I guess, was it by Guido about the future of Python? Is there any record of that somewhere that you can look at?
There's like 4 or 5 different movies. Sorry.
It's on my laptop and I'll upload it.
Okay.
So,
Any other questions?
what's a good resource for sort of module import resolution? You know, like when you're moving Python code from one place to another, and you know, like have to resolve modules. there like a standard way of how you go about that?
So you mean from one machine to another?
From either one machine to another, or one code base to another code base, and like you start missing it into UIs and things like that, or in like these libraries. It's kind of like when you do refactoring of Python code, I've hit that a couple of times, and like it's kind of painful. It's a painful manual process, but I mean, like, are there any tools or anything that can help?
I think there was a bicycle repairman who refactored.